to show the natural convection from the beginning. So I will again do the meshing and case setup for you, and then go for the setting the Rayleigh Bénard convection. Okay. So first, again, this is the repetition what we did. So select the plane. Okay. Then we want to draw a sketch. Okay. Then from the sketch, we can generate a 3D geometry, rename it, and take it to the for the solver, or sorry, mesher to meshing. Then we take the solver and do setup for okay. To do the thing, let's plot a rectangle. Okay, we have a cuboid, so it's let's it 500.5 meter, 500. Sorry, 500. Now sketch is done. Exiting to 3D mode. Now surface is done. Now in the positive z direction, I have the white gravity in negative z direction, because my extension is positive z direction. Go over here, design, pull here. How much? 500. Now I have prepared a 0.5 meter cuboid, right? So let's rename the surfaces. Control select the control, select the surface, then Control G. Its groups are created. Okay. So this rename W. This is here we will provide the heat flux. Sorry, temperature. Control G. This is again W cold. Control G, Control G, Control G, Control G. And then this is W. Maybe I adiabatic one. One side. This is adiabatic 2. This is other. See, now all sides are duly renamed, right? So let's save it. Natural convection. This cube R1. Now the cube is prepared, the naming is done. There is not much more other component that we can do the share topology, anything. So now this is done. We can do one thing. They can change the name. Fluid domain. Okay. So now someone was asking about workbench. Now we'll go to the workbench. This is how a workbench looks like. Okay, under the workbench, we have a lot of Ansys softwares available, just like you have Ansys Fluent, Polyflow, CFX, then structure, etc. We'll go and select the Fluent. Okay. Now in the Fluent, it is asking for the geometry setup. Okay. The geometry, import geometry, we'll browse it. Okay. Cube R1 we have recently created. Select the cube R1. The geometry inputted. Now it is asking us to mesh. Okay. Let's move to the meshing. Meshing. It is taking time to open. Yeah. Now this is the meshing workbench meshing is open. So I hope it will take few minutes more to display the whole geometry. Yeah, the cube is imported over here. Now we have to mesh it over here, right? So you can see the named selection appear over here. Whatever the name you are providing in the space claim is available here. So you can see hot, this is the opposite is the cold, all the things you can see it over here, right? Then to do it meshing on the workbench, so what you need to do, go to the mesh, okay? Display use geometry stating physics preference CFD Fluent, because you are under the Fluent tab opening it. The element size you can put it something around 500, so 50 element you want, something around 5 or 10, something you can put it 5. Okay, export standard, no. Then sizing, okay. Then there are different methods like adaptive meshing, growth rate, just like last time we have 1.2. The feature size, curvature, this is the curvature. If you want to handle the proximity, capture proximity, no. If you want to capture proximity, yes, you can do it. Otherwise, you should accept it, no. If it is proximity, proximity is a size function to edge or face, you should choose the edge. Okay, number of cells, just like Fluent Mesa, we have number of cells, you can put 1 or 2. Okay, this is the global mesh setting. Then we can customize the thing for some particular application. Workbench, we need some particular kind of meshing. Let's see what are the thing. Insert method. What method of meshing you need it, right? There is some automatic method. Okay, so I just first thing geometry selection. I just go over there. This is the geometry body selection. This is the face. This is the edge. This is the node. Geometry selection. I select this geometry. Geometry selected is there. Then a method is automatic. Suppose if I assume automatic, that's means remain it as automatic. Allow it. The solver, sorry, the Fluent workbench mesher will do some automatic mesh. Let's see how automatic mesh looks like in this. Generate. Done. The mesh is done. Here you can see you have a very structural mesh. If it is, or because it's a cuboidal box, it's automatically created a structure mode of mesh over here automatically. Okay. So if you want more control over automatic mesh, just like you have a option like tetrahedron, hex dominant, sweep and all. Let's go by the sweep mesh. Let's see. Sweep mesh is kind something. If you have a surface mesh, want to extend it in a lateral direction and cut it, then the sweep mesh method is basically the good method, sweep mesh. Okay, now first clear the generated mesh. Okay, so you have a sweep mesh. Okay, body selection, this one body is selected. For the sweep mesh, we have a method that algorithm is a program control, use global setting automatic, but we have to choose the source and target. Let's manual source and manual target. Suppose that I want to, this is my hot surface, hot. Okay, so suppose I want my source to be this hot surface. I'll go to the surface over here, select. It's a manual source to target. This is a hot surface. Okay, if I want the cold surface, okay, if I come over here, okay, I can select the cold surface. This is done. Okay, then face type, the hot surface meshing, what are the things? It is telling quad, tri. If you want the triangular element or quad triangular mixture element, you can choose only quad. That is also find all quad element, right? The number of division means the total number of division, they can be split into the geometry, number of parts. That also you can define. Here we can define number of division default. So something defined 500, let's put it around 100, 5 mm each. So no bias. If you have a bias factor, then something mesh stretching you can see something some bias factor. If you define very fine over here and gradually at the center it will be coarse again. It will be fine here towards the center. It will be coarse. Okay, let's see how it looks like. You can see the progress here. Yeah, see the mesh is generated over here. Okay, so here we have not given any prism layer and anything. So if we like, we can also introduce some prism layer. Okay, so let's do that. The method, instead of this sweep, if I call it automatic, okay, clear generated data. Okay, if I need the prism layer across my boundary, what I need to do? Yeah, automatic insert this inflation layer will be there. Yeah, this is the inflation layer. Okay, so scoping method, geometry selection, this geometry we need to. So geometry boundaries or scoping method, geometry selection. Okay, then we have to select the faces, all the faces across which we need to develop the prism layer. We select it, apply geometry, smooth transition. There is maximum number of layer is 5, transition rate 1.2. If you like, you can put it 1.1 or anything, in person 3. Okay, there is a lot of option in the geometry. The first layer thickness, total layer thickness, aspect ratio. In Fluent method by default is the aspect ratio. Okay, here there are 3-4 options available. Smooth transition, even if we select smooth transition. Okay, let's see. Because of the prism layer, things are getting delayed, but anyway, it will perform the meshing. Yeah, the meshing is done. Now you can see the quad element are not formed. This is the, I think, tetrahedrons element are formed inside the thing. So how to see the inner thing? So there is something, clip plane will be there. Display. Random display cross section. No, not this one. Clipper select, extend, upload tags. Yeah, section plane. This is a section plane is there. We can go and select some section plane like this. Okay, now it will show the mesh structure here. You can see here the mesh count is more towards the tetrahedral. Okay, prism layers are formed adjacent to boundary. Okay, and the mesh is more just like a tetrahedral element. It's not a poly and all. The mesh count will be high. Okay, yesterday was someone asking. So here it's possible some are tetrahedral mesh, some are hexahedral mesh based upon the setting 3 4 you have 3 4 zone in, you can generate different kind of mesh in different zones here. Some are sweep mesh and all. Again this will be mesh count will be high. Okay, so for the natural convection we can make some polyhedral mesh which will be computation will be faster. This is just for description how to do the workbench meshing. So hopefully you have gone through the environment over here. Okay, and the mesh, uh, to see the quality and all, this will give you the information. Okay, check your mesh quality and statistics. Okay, this will give you the number of element. This is around 2,22,000. No, this is 22 lakhs 20,623. This is around 2 million mesh count is permitted. This is huge. If you do it poly, the less number of mesh will be generated. If you see the tetrahedron mesh, it's around 2 million, 2.2 million mesh is generated, right? And also you can see the mesh statistics over here. This will give you the, it's a good mesh or a bad mesh, the quality. Okay, so this is all about the workbench meshing. Okay, so let's shift to the fluent meshing. Do the same meshing in the fluent and do the case setup for the natural convection. Okay, you see it here, it's around workbench doing the tetrahedron, it's around 2.2 million is the mesh count. In a, means it's a rough exercise, whether means not precisely optimize many of the parameter, but it's around 2.2 million. Okay, so let's exit it here, workbench. So any other doubt in the workbench, or we should go to the fluent meshing? Let's move to the fluent meshing then. So same, instead of forced convection, I should go to the where natural convection. WhatsApp, natural convection, yeah. This is not solution, this is meshing. Double precision, meshing processor single, solver processor, let it make it one. Meshing double precision, you are solving the mesh information. Okay, meshing. Outline, file, import, CAD, cube R1, shaped mesh. So minimum size you put it 1 mm, maximum size you put it 5 mm, 100. Okay, it's 10 mm you can put it. So proximity you can choose it, maximum proximity you can choose it 1. So import. Now the mesh is imported. As usual, the method for checking over here, you can draw it. Fit to window. Okay, this is the mesh that is imported in the Ansys Fluent mesh. So you can check the quality over here. Summary, what is the mesh count? The mesh count is around 34,000. If I make a poly mesh, almost 3 to 4 times, it's around zero point 0.1 million. It's going to be 0.1 to 0.2 million. It's going to be generated the poly, while it was 2 million, 2.2 million in the tetrahedral mesh. Okay, so the maximum skewness is 0.35, which is acceptable. All faces is around 34,000 faces, so nothing much to worry about the surface quality. It seems surface quality is okay, maximum skewness. So then compute. Okay, I computed the region. Then the regions come out over here. I just need to change it to the fluid, assign it to the type fluid, manage, rename. If I record, I can rename it. The initial things I can remove it. Okay, so now go to the auto mesh again, same scoped. Okay, select wall, prism wall, aspect ratio 10, number of layer 5, growth rate you can put 1.1 or 1.2 something. So grow zone, selected phase zone, then select the zones in which it will grow. So all are wall, okay, even if it is hot and cold, this is a wall surface. So select all, okay. This is created, the prism is created. Then here, what will go? We'll go for polymeshing. Compute the size. So let the size, put it maximum be 10. So then apply. No problem, no issue, mesh. Okay, the meshing is done. The quality measure has been set to inverse orthogonal quality. Let's see what is the summary, total the mesh count, etc. Okay, the mesh count is around 22,71,791. It's around zero point 0.2 million. While in the TET mesh, it was creating around 2.2 million. Subsequent, drastically, almost 10 times, we reduce the mesh count by the poly mesh. This is advantages in terms of the computational effort, right? And the maximum cell quality is zero point 0.6, which is acceptable. Let's see how it is looking. Yeah, this is my poly mesh. Okay, this is a very good mesh as it looks. Okay, let's see how the boundary layer is developed, if it is collapsed or not. So to do that, what you do, insert clipping plane. Okay, any plane you can choose it. It says symmetry in all direction, I guess. So now draw the cell layer. Yes, boundary layers are developed. So then I have a poly mesh inside. Okay, this is a poly form of elements are inside. So now meshing is done. I need to save my file, write mesh. So yeah, cube r1 msh.gz, I put it. Okay, done. So now insert clipping plane. So now from the Fluent itself, you have the option directly go to the from the measure to the Fluent setup. How? Here switch to solution. Okay, be ensure you measure quality everything. Okay, before going to the solution and save the mesh, because you cannot come from the solution to measure again. Okay, switch to solution. It will ask you to ensure everything is saved and all. Yes. Now the message transferred to the solution. Now let's see, do the setup. Now the mesh display, display. This is my geometry. They successfully transform into the Fluent. Okay. What the first thing is to scale, right? So it is showing everything is 500 meter. This is not the case. 500 meter means it's a big domain. So we need to choose the mesh is created in millimeter. Scale it. Yeah, 0 to point. This is a 0.5 mm is the diameter. That is correct. Then check the mesh quality. It is correct. Nothing wrong. Then evaluate mesh criteria. Quality check. Inverse orthogonal quality. It's fine, right? There is no error or something. Now we have to do the natural convection simulation, right? So let's see. So again, it's a pressure base because the density is not a strong function of pressure. Okay. So it's a natural convection, density is a function of temperature. So it's a pressure base, steady state. We have gravity terms, we have to be switch on because it's a free convection. Gravity is in which direction? Okay, gravity is in negative z direction. If you look, we have hot oil, gravity is in negative z, the opposite direction. Z is in the, this is the z direction minus of g. So here we can put x0, z0, the gravity value minus 9.81, we can put it, right, meter per second square. So the gravity we have formulated. Again, we don't have multi-page. We don't have multi-page. So energy equation, it's a natural convection. Density is a function of temperature. So energy, you go it. Energy equation, you switch on the energy equation, right? So by default, it is viscous, as I told. It's a viscous K omega SST. Okay, low Reynolds number correction. Okay. So viscous heating, if you have a viscous heating and dissipation kind of thing, you can switch on it. Then allow the rest parameter as default. If you have already some experimentation, if you want to fit the result with experimentation, you can play with this parameter. Otherwise, you can leave it as the default setting. So if you want viscous setting, you can choose it. Otherwise, leave it, right? So these are all turbulent parameter is set. Now the thing comes for what? The things come for radiation. If you have a radiation augmented with natural convection, you can select the radiation. Then there is option for different model of radiation, just like discrete ordered method, surface to surface method, or P1 method. Okay, this discrete ordinate method is just for the participating media radiation. Suppose you have some carbon dioxide kind of gas which actively participate in the heat transfer mechanism. Okay, they absorb, they emit, they scatters. This is kind emit participating gas. You can go for discrete ordinate. If you have a surface to surface radiation, in between air is there, air doesn't participate much into the radiation process, you can go S2S radiation. Okay, if conjugate problems there, then the nothing much here to put in the models. So let's come to the materials. Okay, what is the material? Air. So then you need to, the parameter is that density is no more a constant. Where density is constant? Density is constant at the left side of the Navier-Stokes equation. The right side buoyancy term, density is varying. Okay, this is famously called as Boussinesq's approximation. The density variation is linearly proportional to the temperature difference. Okay, this is called the Boussinesq's approximation. Okay, so the density, instead of the constant density, there are a lot of other things. Okay, just go for Boussinesq. Okay, you must have known about the Boussinesq. What is the Boussinesq? Means it is density is a linear function of temperature. Okay, G beta LQ. Then rho is equal to rho 0 into 1 minus alpha into delta beta into delta theta, right? So give the reference density. It's around again 1.125 or something. Reference will be there. This is specific heat. Nothing to bother change the default specific heat. Thermal conductivity. Okay, this is the viscosity ratio, and this is the thermal expansion coefficient, right? This you need to be calculated. What is the thermal expansion coefficient? So let's go to the paint first. Okay, so this thermal when we are solving the Boussinesq approximation, rho equals to rho 0 right? So this beta is the thermal expansion coefficient. Normally it's beta equals to 1 by absolute temperature. It's a reverse of the compressibility, inverse of the compressibility. It's a compressibility, right? Inverse of the absolute temperature beta. But again, it's a parameter which you need to supply it, right? So suppose you are solving a natural convection problem, you are dealing with the Rayleigh number, okay, which is the band force to the viscous force, okay. So G beta LQ delta theta by nu into alpha. This is the definition of the Rayleigh number, right? And you have a Prandtl number. If you are doing a natural convection, this is a fluid property. For air, it's around 0.7 or something. This is around nu by, oh, it looks like gamma, but it's a nu, okay. Nu by alpha. Momentum layer thickness to the thermal layer thickness, right? So from here, suppose your Rayleigh number is 10 to the 6, Rayleigh number is 10 to the 7, Rayleigh number 10 to the 8. Now, what dimensions you have already fixed it? You suppose you fix the fluid, means Prandtl number 0.71, you fix it, the fluid is around air at a particular reference temperature. Then this nu and alpha, they are become the constant. You cannot change it over here, right? Rayleigh number, you put it turbulent for turbulent, its Rayleigh number is 10 to the power 8. Okay. Nu into alpha, they are also constant. Okay. You can have the value of nu into alpha from the table. You can get at a reference temperature 30, 40, whatever the temperature you put reference. At that temperature, you can determine the nu into alpha. This gravity, this is again another constant, right? Then this LQ, you have already chosen the dimension of the cavity in the temperature gradient direction. Its L is the dimension, so it's around 0.5. This is also fixed. The only parameter that is available to you to make changes is the beta and delta T, means how much compressibility effect you are providing and how much temperature difference you are maintaining. Suppose temperature difference, you put it around 30 degree. Okay, now you can compute and find a particular value of beta, right? The compressibility thing, right? So this you can compute based upon your Rayleigh number and temperature difference. Once you set up the temperature difference 30, 40, for each temperature difference, you will get a single value of beta. Okay, so that beta you need to put it over here. Let's put some not exact calculation, some arbitrary figure. So you may be calculate it later when you are doing your simulation change. Now all the parameters are defined, so make sure if you have choose the Boussinesq approximation, make sure to find out the value of beta from your rough calculation and put the value of beta over here, right? Done. So then cell zone condition, this is the fluid, nothing much change. Okay, then there is some change in operating condition, right? So cell zone condition, this is somewhere operating condition. See. So this is the operating pressure, right? So gravity you have choose, operation temperature. This is the reference temperature in which you have determined all the property, just like rho zero, alpha, nu, all the property at some particular reference temperature you have determined. Now specific operating density. What is this? Okay. So specific operating density means the you have a term over here. Okay, rho equal to rho 0 into 1 plus beta and delta theta. This is specific operating density because the buoyancy force on the Navier-Stokes equation will become like this. This will be rho minus rho 0 into G. So the convection will take place whenever there is a difference of density from the reference density, right? So this is known as operating density. Okay, this means as per the approximation, when you are solving the Navier-Stokes equation, rho substantial derivative of u by dt, you have a lot of set of RHS. It is assumed that the density is not varying on the left side in the Boussinex or the normal approximation. So that's why this is rho 0 here, right? Whatever the density variation, it is only variation is occurring in the buoyancy term, not other places. Okay. Otherwise, based upon the temperature, density will change everywhere. Which density will change? Take this reference density you will take at the left side, right side only during the difference between the reference density to the density at particular place due to temperature, that will gives the buoyancy effect. Okay, so that is done. So this is the reference density. Okay, whatever will be the available density, it will subtract that from the reference density to calculate the forcing. Means this into multiplied by the gravity, this will give the forcing. Okay, then boundary condition, right? Here all the boundaries, they are what? Here all the boundaries, they are wall type. No need to change it any type, rather than define the condition. Come to W hot wall. So thermal, it's a stationary wall. It's a wall, nothing. So again in the thermal, it will ask you, okay, what kind of boundary condition? Whether you are providing the boundary condition of constant heat flux, constant temperature, or it's a mixed boundary condition, right? So here I am giving a constant temperature. Let's temperature, it's around, this is the hot wall, right? I am giving it's a 320. 320 or 330, you can put it. Okay. So this is the hot oil is 330. Similarly, the cold oil, 300. Okay, 30 degrees difference in temperature. I assume, okay, the cold oil is at temperature 300. The rest valve, adiabatic, the flux by default, the thermal condition is that heat flux equal to 0. Okay, so you leave it. Now the case setup is done, right? So what are the rest? So heat flux, reference method, here you can go to methods. So whenever you are using the natural convection, be sure you are enabling the coupled scheme, because in the same matrix it will compute the pressure and the velocity. It will couple it. So not like simple, it will again gauge the velocity and correct the pressure, because if you correct the pressure again, that will affect the density and all. So then it's better to go for a coupled, which is non-oscillatory. Okay. So control, here you can choose the upwinding scheme. Okay. So I just put it initially 0.25 or something, curve convergence 0.3. Report. What you need? You need new. Okay. Whatever flux report you need, how much heat is going from a hot surface, how much heat is going to a cold surface, right? This is a flux report, total heat transfer rate, which surface, hot and cold. Okay, per zone you can put it, report plot, heat transfer. Auto save, again after every 100 iteration or something, auto save. Retain maximum 2. Then run calculation, time scale factor, because you have chosen a pseudo transient, it is asking for a time scale factor. Okay, if you don't choose a pseudo transient method, pseudo tangent. If you don't choose it, that's also fine. You just give the number of iterations. Suppose I give 1 to 1000, 10,000 iteration reporting on trouble 1. Okay. Let's say the case file. Done. Now let's calculate it. Okay, it's asking to be initialized before it started. Yes. If you give it, it is doing hybrid initialization. Now the computation started. Okay, it may be diverged because randomly we have given some beta. That work we need to do with pen and paper for a particular Rayleigh number. It's taking time. The whatever heat is coming from the cold, it should be sorry, hot plate, it should go to the cold plate. So you make sure this should be balance each other. Okay, the heat balance should be there. Whatever heat is coming, it should be go away for the conservation of energy conservation. So it's take time. The residual will fall 10 to a minus 4 minus 5. Then the solution will be converged. So let it run for few hundred iteration. Till that time, we can take some question. Then we'll come to different models, other models of the natural convection. Okay, apart from the Boussinex. So now we can open it, madam. We can Gayatri, madam. We can open the session for the questions for the participants.
Sir?
If any question, we can take the question till it was running.
Any questions from participant side? You can unmute yourself now.
Hello.
Yes.
Good afternoon, sir. Sir, now whatever the case you have discussed, now that is for natural convection. So what
Yes.
are the changes we supposed to do in modeling if we can choose the same problem as a force convection? Like velocity or Reynolds number is theoretically that is the part we have to add now. So what changes we supposed to incorporate in order to solve the similar problem with force convection?
So Venkatesh, your question is not clear to me. So what's the question is? What exactly your question is?
Now the models which we have selected, no sir, right now. Boussinex, we have one thing we have selected for natural convection. If the same problem, if we can solve for the force convection, what are the changes in the different overall settings of the problem?
Okay, what exactly force convection means? There is some external source for the movement, right?
Yes, yes.
Natural convection, the buoyancy drives the flow. If it is force convection, there should be some external movement that drive the flow. Just like last session we have seen, there was a rotor or the blower that drives the flow, right? Here in this cavity, what you want me to set? Which mechanism you want me to force the flow to be?
Like if it is a assume that the whole thing is closed things and externally some velocity is blowing on it.
Okay, lead driven cavity. You want to talk about lead driven cavity? Okay,
kind of
that's
that with the force convection.
Yeah. Okay, we can say it. Okay, let's see. So now it's I think converging very fast. So let's stop it. Let's see the result and set the force convection. Okay. Okay, now it is done. graphics, contour. If you can see, want to visualize the velocity, etc., you can see it. Okay, you just need to create a plane for that, to where to see the thing. So you can go over here, create surface, create plane, you can create it. Okay, so which direction you need to create a plane, just look at here. Okay, if I this z direction, so I need to xz, either xz or zy in the direction. If I need a plane, then it's fine. Okay, so choose any of the axis, axis. So yz plane is fine for me, yz plane. Okay, yz plane. So x at a distance 0.25 means it's a mid distance. Okay, so surface one, its name gives something around visual surface, visual one or something. You give it. Okay. The surface is created. Okay. Now contour. Yeah. What contour you want to see? You want to see the temperature contour. Okay. Static temperature. Okay. Which surface? Visual one. Okay. Okay. Let's rotate it, fit it to the window. It is showing 300 to 330. Which surface we have done? XZ, right? This is XZ, Y plane. Let's put it. Why it is not showing fit to window? It's yeah. It's not yet started. If you look, it is not, a convection is not yet started. Only in the vicinity. Okay. Then because it's only 32 iteration is there. If you allow it, you can see how the plumes are rising over here. Just now it is showing that temperature is here, it is started diffusing. Convection is not yet set. It will take time, at least few thousand iteration to set. Again, you're coming to a question. Okay, we can allow it. Coming to a question, how to model it as a forced convection, mixed convection. Okay, I cannot tell it now a forced convection because we have a buoyancy effect here. We have a force convection component here. So it is a mixed convection, right? So both buoyancy and the external mechanism that drives it. So to do that, so what I need to do? Okay, suppose my cold wall is a lead driven cavity problem. My cold wall is moving, right? This is hot wall, my cold wall is moving, the top wall. So go to the cold wall, there is a momentum, okay? Then it is telling it's a stationary wall, right? Now you can make it a moving wall, right? Then it's which direction it is moving, okay? Suppose this, let's display the whole geometry. So this is the thing. Suppose your cold, this is my cold wall. Okay. Suppose it's moving in the y direction. This is moving in the y direction. So put the direction over here. Y is equal to 1, x0, z0. So it's moving in the positive y direction. So it is translational, rotational, the component. Suppose it's a translational component speed. So let's say moving with a speed 0.05 meter per second. Okay, that is fine. Then roughness and all, this is the optional parameter. If you have a rough surface or smooth surface, this is no slip condition still prevails. Okay, so now this is a condition of the mixed convection, right? Moving. So means you have now the flow is determined by somewhere Richardson number. So Richardson number something defined the strength of the natural convection to strength of the forced convection, which is more dominant. So if natural convection is more dominant, it's around more than 1. If it is forced convection more dominant, it's supposed to be less than 1, right? Now you come and start the calculation again. Now it's a mixed convection problem. Your wall is moving, also you are hitting from the bottom. So did I answer your questions?
Any other questions from the participant side?
The last question was from this answered this last question, right?
Venkatesh sir?
Any other, I forgot the name who asked the last question.
Venkatesh sir.
Venkatesh, are you satisfied with the setup or still any doubt is there? So there is no meaning to go further without clarifying the doubts. So ask me. You are not audible. Not audible.
Fine, sir. I got it now. Another point is, sir, what is the capacity of systems or computer specification you are having? Because 2.2 million cells was generated now. So what is a typical specification required for this kind of simulation?
Again, this is a laptop workstation. I guess it is around 16 GB. This is laptop we use only for the post processing, just documentation work, not for the computation. Okay. So in the Paris we have a supercomputer. In Bordeaux we have a supercomputer. Once a case is set up over here, we send the file there for running. It's around 100 200 core it is run, and based upon the turbulence LES, it runs for days, it runs for weeks. So based upon the thing, so on an rough estimate for the Fluent, so you need 1.2 GB of the RAM, around 1 to 1.2 GB of the RAM for each 1 million mesh. Suppose you have a cavity having 4 million mesh, you need around 6 GB of RAM to dedicated to Ansys for the computation.
Okay, sir. Thank you. Thank you, sir.
And again, it's specification because 7 years back when I was doing postdoc in US, so the workstation size was around 512 GB. 512, not MB, 512 GB is the RAM. With that RAM, we are doing some biological fluid flow processing kind of computation.
Okay, sir. The idea was even workstation which I have used during my research, it was 64 GB RAM, 32 core systems. For combustion, it is to take 3 days time, at least 3 days time for combustion simulation.
Yeah, because more complexity. Yes. You have more complexity, chemical reaction. You have a lot of other things.
Correct. So that's why on that note I have asked, because there we have used only max 5 lakh cells for a sector.
0.5 million.
Yes, yes, sir. For a cylinder with a sector we have chosen for in-cylinder combustions, and time is to take at least 3 days. For
it's depend upon how much time step size you are taking. If you are taking a very large time step, it's computationally going to be do very fast, but maybe your numerical stability will be an issue. There may be a combustion, some different time scale combustion physics will be there. The reaction is happening, you are taking some different time scale. So you have to keep in mind all those points, how to simulate a transient simulation with the time step sizing.
Okay, sir. Thank you. Thank you, sir.
Any other queries?
Any other questions from participant side?
No other doubt. I guess everyone is thorough and fluent then. Please feel free to ask not necessarily to this session. Even if you have some queries from the previous session also, please feel free to ask. Particularly if you are facing any trouble in your research, you want particular kind of problem in mind in which you like to be addressed during this session, so that it will be helpful for you, you can feel free to ask. We have another 30 minutes of time till this run is at least some progress, so that we can post process it. So we can take some more questions. No more question?
Sir, I think you can continue, sir.
Okay, thank you. So let's stop the run over here. It will take 8 days to at least couple of hours to complete. So we can stop it here. You know the process. You can now do the run. So let's come to the other physics actually. So here you can see the temperature. Again, it's see, once you give the force convection component velocity, the symmetric is breaks. Earlier it was symmetric plume was coming. Now the symmetry is breaks. Now the convection, let's see the velocity, how it is there. This is the temperature contour. Let's put it x-axis. Oh, okay. So come over here, put the velocity magnitude display. Okay. It's a why it is 0. We have given it some, yeah. This is the velocity because it's not yet started. This plane moves with the velocity hot while we have given some velocity. Okay. So this is a lead driven cavity kind of flow. So gradually it is diffusing the velocity. It will come like a rotational structure. You can see this is a structure kind of see because of the lead driven cavity. So it will take some time to generate the result. Okay, in a 3D. So now come, there is a earlier this simulation. Let's switch on the stationary wall, make it stationary, focus purely on the natural convection. So okay, so what we did over here, we just in the property we assume it's a Boussinesq fluid, right? The Boussinesq fluid, what's Boussinesq approximation? Already I have explained it over here. Boussinesq approximation here. Suppose your temperature difference is too high, it's around 100 degree or 120 degree centigrade. So if for such high temperature difference between the hot and cold wall, the Boussinesq approximation doesn't work actually, right? So it gives the result very different from the experimental result, right? The temperature, the density difference is a linear function of the temperature as long as the temperature differences remain small, 30 degree, 40 degree, 50 degree. If it is too high, then it is very difficult to handle those things with the Boussinesq approximation. Then there is another concept called for density, that is called incompressible ideal gas. If you open it, there are a lot of things are there. Constant ideal gas. Ideal gas we cannot solve it because it's a PV is equal to nRT. It's an incompressible ideal gas because here the flow is itself incompressible, right? So incompressible ideal gas, okay. Then incompressible ideal gas, the density is no more. You can have the field, the density field, it is somehow freezed. You don't have option to give any reference density. where it will find the reference density. The other parameters as usual remain constant. You can provide. You can see the two changes. When you are giving Businix, you have to give the density, okay, reference density, as well as you have to give the thermal expansion coefficient. But once you are giving incompressible ideal gas, the thermal reference, this one, Businix, instead of the Businix, if you give incompressible ideal gas, the in beta, the expansion coefficient, that field is gone away. The reference density field is freezed. So instead of that, you get a new field over here, property field, that is called molecular weight, right? Then let's see how it's doing the thing. Okay. Then you go to the shell zone condition, operating condition. Here again, it's operating pressure. This is something operating temperature, right? So this is operating density. So what it is telling, the incompressible ideal gas. So normally ideal gas equation is PV is equal to mRT. This is the equation of state, right? So P is equal to, if I divide it, this is rho R T, right? So then what is rho? P by RT, right? This incompressible ideal gas, when you are choosing this option, what theoretically it does, so it fixes the temperature, sorry, pressure. It fixes the pressure in this equation. What is that pressure? This fixes the pressure, operating pressure. Your operating pressure is kept constant by choosing incompressible ideal gas, right? Then anywhere your temperature is changing, okay, that time your density is also changing, temperature is increasing, density will be decreased, right? Then R, this is the universal gas constant divided by molecular weight. This is the characteristics gas constant, 8 point something divided by molecular weight. Suppose you have air, you have nitrogen, you have hydrogen. For every individual gas, the molecular weight will be different. So you have to divide that with the universal gas constant. So universal gas constant, something I put it RU. Then RU, this R is equal to RU by molecular weight. R. This is the characteristics gas constant. Okay. So this density in the Navier-Stokes equation, that is determined where? That is determined from the, here you will get a convective derivative, substantive derivative, here pressure term, then you have a diffusion term, this is a pressure gradient term, then a momentum diffusion term plus rho minus rho 0 into G, right? This rho, okay, this rho is now computed from where? This rho is now computed from this equation. Sorry. This rho is now computed from this equation for ideal gas equation, incompressible ideal gas equation, right? This rho 0, where is this rho 0? This rho 0 you have supplied here, operating density at a particular temperature. You know the reference density that you are supplying here, right? So by choosing the incompressible ideal gas, you are allowing the density variation in the left side of the Navier-Stokes equation as well as in the buoyancy term, right? In the inertia term as well as in the buoyancy term. That's why, so the density, we during the Businix approximation, we assume the density is a constant. So suppose we put it at equal to 1.1, the density, air density may be 1.1 if you do the experiment around 25 degree or 26 degree centigrade. But someone is doing experiment at some high temperature. Let it it's a furnace around 600 degree centigrade. Okay. Foreign reference density is different, right? Suppose the furnace temperature vary from 600 degree centigrade to it's a 1200 degree centigrade. It's varying another 600 degree is the difference of hot oil and cold oil temperature, right? So during each grid, okay, when it is coming, the temperature may be 600, here may be 800. At 800 degree centigrade, my air density is very different that my air density at 600 degree centigrade. But the Boussinesq approximation, what I am assuming, the Boussinesq approximation, I am assuming the density is constant in the left side, inertial part of the Navier-Stokes equation, the convective acceleration term. So this is going to give you error if you have a large temperature gradient, like 600, 1200 kind of thing. If it is 30 degree or 60 degree, then the change in density due to change in temperature, it's point some 2 decimal or 3 decimal points. So that doesn't affect much your computation. But when you have a large temperature gradient, 500, 400, 600 degree centigrade, the density term in the Navier-Stokes equation itself changes with temperature. That you need to take care, otherwise your simulation will not going to give you a good result. To compute that one, this is the variable density or the formulation, which is known as also incompressible ideal gas formulation. So every point you need to calculate your density. That density is going to your momentum equation. That density, from that density, any difference in density with respect to the operating density is giving you a buoyancy term, right? So this is the method. So it's somehow more accurate for natural convection simulation when you have large temperature gradient. Okay. So similarly, there are some people, they are doing some explosion or blast modeling. So there are some other form of density also exists. Okay. So this one, Peng Robinson, lot of other things. Those are studied advanced chemistry. They can understand what thing is happening during blast or explosion. So they can go for higher polynomial order of density and all. But for natural convection, either it's a Boussinesq or incompressible approximation is sufficient to do the simulation. Okay. So by setting those things, the rest remaining position setup is exactly identical. Only you need to change the incompressible ideal gas and set the property in the operating desk. So here, just like you can calculate your equivalent Rayleigh number, this one, your Richardson number, everything you can calculate in a non-dimensional form, and whatever the quantity you can put it back over here. So Rayleigh number definition is somehow your buoyancy force to the viscous force. So you calculate the buoyancy force rho minus rho 0 into g, then calculate the viscous force nu into the gradient. So if you in that case, if you equate, you will get your Rayleigh number here. For a particular Rayleigh number, you will get what's supposed to be your reference temperature and operating density, right? Your operating density is the variable here. So to get that, you will find the temperature. So you have to choose our reference temperature accordingly to match that Rayleigh number. Okay, and or temperature difference delta T. In the Boussinesq approximation, we have two parameters. One is beta, one is delta T. That are used to interchange to get a particular Rayleigh number. But here, incompressible ideal gas, that beta terms is gone away. Okay. So now once you choose the operating pressure and operating temperature, right? Now only variation is delta T. Okay. that eventually comes into your Rayleigh number to determine the magnitude of the Rayleigh number, because L and other parameters, they are almost fixed geometrical parameter. So this is what the end we can see the natural convection all about. So there are a lot of whole other things. This is just some beginning introduction to the natural convection modeling in the Ansys Fluent. So you can practice a lot of tutorial. So you can do the research problem in natural convection 3D, 2D. So the more you practice, the more trouble you will face, and you will come to learn more. So unless you practice these things, you will just listen and forget. Nothing will be useful. So you have to do some tutorial yourself to understand what's going on and what's the trouble and which model to find out. So I think we come to the end regarding the natural convection. So yeah, make sure that your Rayleigh number is more than 10 to the power 7, 6 or 7 in between transition occurs from the laminar to turbulent flow. So if your Rayleigh number is more than 10 to the 7 or 8, so it's going to be a turbulent region. You just go for the turbulence model like K omega SST or K epsilon, any model you can choose it and do the simulation. Again, K epsilon has 3 different categories: realizable, RNG K epsilon, realizable K epsilon, standard K epsilon. Anything you can choose and go for modeling. So if any question, I love to answer those questions.
Is there any questions from the participants? You can unmute yourself. Or you can raise the hand.
No more doubt?
Sir, this is Venkatesh here.
Yes.
Sir, whatever the physics we have for normal things, all the mathematical things we have, like fluid mechanics, derived formulas and all, if you come to the microfluidics part, then what are the special things we supposed to take care doing the modeling part? Because normally, if it is fluid through the pipe, no, Hagen-Poiseuille flow, normal equations we have. But for microfluidics, no, physics may differ, no. So
yes.
Is any model or any sessions you have on that in future, tomorrow or day of tomorrow? So one request is from my side, please handle that also.
Again, microfluidics is a very big subject itself. I cannot tease that microfluidics as a whole in this introductory CFD session to turbulence. Okay. First of thing, you don't have turbulence in the micro scale, right?
Yes, sir.
The flow is laminar.
Yeah, no reduction.
Second, the physics changes. You have a slip boundary condition, Navier slip boundary condition kind of thing. Okay. So I will recommend you to go to the lecture series by Professor Suman Chakravarti that is available in NPTEL. He is my teacher also. So you go through his lecture series, then you will find it more about the microfluidics, the physics and all, because without understanding the basic physics, it's very difficult to understand the theory understanding the theory. It's very difficult to do the problem in Fluent on the microfluidics, because
Actually, we have I have floated elective for PG students, sir. Last time, from last 2 years, we are teaching it. Same Chakrabarti sir series as his book also we are referring. But simulation part we have not done yet. So that is
because simulation is a research part, right? Simulation is a research part. You are teaching his NPTEL lecture series book. That's a good. It's a theory. Simulation is a research part. Suppose he solved lot of problem on lab on a chip or a disk. He doing the blood flow. It's a very diffusion process. The Navier-Stokes equation, they have simplified. A lot of assumptions are there. All those flow in a micro channel. So recently we are solving some biological flow with Professor Suman Chakravarti and one of our undergraduate student. We are working together. Some flow in the brain cell for the dementia modeling. So you have some memory cell, blood flow is going. So if blood flow is not proper, you are started forgetting something. It's disease. So just like you can tell Gajini, your short-term memory loss kind of thing is happening. So those things we have some clinical data. Now we are modeling with the undergrad student is working. We are doing modeling for that, the short-term memory loss Gajini disease.
Well, sir, thank you.
So there we are doing platelet activation. If there is a stroke in your brain, how the blood will be clot there. Those things we are doing, and these are very difficult to explain it in a generic platform like this, where specific application is to the CFD beginners or the turbulence.
Okay.
Any other question? Chandrasekhar is there or no? Sujata, Chandrasekhar, they are there.
Sir, I'm audible, sir?
Yes.
Okay. Any other questions, participants? I think no more questions, sir.
Yeah, then we are end of the prescribed session. So if tomorrow I have to check, is it's possible, I will let you know today by afternoon. So we may have a session on short session on UDF,
okay.
the
Okay, sir. Okay, sir.
user defined function in Fluent. If you have some additional exercises that you need to do, some additional source term you need to provide, you some bound kind of time dependent boundary condition you have to provide. So you have to write your own C program and compile it and link it to the Fluent library, so that Fluent will do some computation for you. So this is UDF. So tomorrow we are going to if situation means permissible, I am going to introduce those things. So may not be in details, because again learning UDF it takes another 7-8 hours of classes. But again I will give a short description what UDF and how to compile it, how to link it, how to write, what are the macros, some short description, so that it will make much more sense for the user to use those to whenever they need it. So today afternoon I'm going to confirm you the same. So let's I will have to fix my calendar for tomorrow and we'll update you today.
Okay, sir.
Afternoon.
Okay, sir. Shall I end the session, or do you want to continue this?
Participants, please all of you unmute your comment, turn on the video so that we can take a group photo.
Yeah, I stopped sharing.
Thank you, sir.
Okay, hope you learned some basic principle of fluid mechanics, turbulence in this workshop, and also gain some idea about the computational fluid dynamics setup using Ansys Fluent from the geometry, meshing, and setup. Hope it will be helpful for you for your research. So, okay, if you have any more doubts, we can couple of minutes to discuss. If not, we can end the session. Then we can meet tomorrow. Okay, Gayatri, it seems like there is no more question. We can end this session.
Yes, sir. Yes, sir. Okay. Thank you very much, sir.
Thank you. Thanks, everybody. Wish you a happy weekend.
Participants, tomorrow we have next session at 9:30 by Professor Andy Chan. We'll meet tomorrow at 9:30. Okay, thank you, sir.
Okay, thank you. Bye-bye. Bye.
Bye, sir.
Thank you.